Hi, my name is Travis. I work for Kaiser Permanente in California, and I'm recording this from my garage with a couple of dogs at my feet. Here are the learning objectives, which I will hit on as we go. So, I don't think that net zero hospitals are a myth. I think they're attainable in the near future. Our moderator, Frank, asked me to talk about the codes. So first, I'm going to say that most of the energy that we waste in hospitals is not really code related. It's related to our design practices. So as design engineers, we're going to need to take responsibility and do what we can, stop blaming the codes. And then secondly, I am going to critique the codes. I'm going to tell you that some of the concepts in ASHRAE Standard 170 are silly, and I want you to notice that God will not strike me down when I'm saying those things, because it's okay to critique the codes. Many of our designers treat the codes like they're sacred. It was written by people that were smarter than you, and I assure you it was not. So first off, let's put hospital energy in context. I'm going to show you about 5 pictures in 4 minutes. This first picture is energy consumption or energy signature of U.S. commercial buildings by type, and you can see office buildings, churches, and lodgings, and hotels, and wow, what the heck is that? That's inpatient healthcare. Ouch. I always like to point out hotels because hospitals and hotels both have sleeping rooms and they run 24/7, and a patient tower uses double the energy of a hotel. This next picture shows U.S. hospital energy consumption versus other countries, and we're winning or we're losing, depending on how you want to look at the picture. Our energy signature is at the top. Canada is right there with us. We use about 1.5 times the energy of a general hospital in the UK, and about triple the averages in Germany or France. Then this picture is a pie chart that shows how we use energy in U.S. hospitals. This may be a little counterintuitive if you haven't seen it, because our energy is not the medical equipment in the hospital. It's ventilation. 2/3 to 3/4 of the energy in a hospital is heating, ventilation, and cooling. And the single biggest use of energy that we have is reheat energy. And then this is why we have so much reheat. We design hospitals with a legacy methodology called air changes per hour. There's a table that tells us how many air changes to use for nearly every space. This design method drives our energy use. And I don't know if you've ever met any design engineers, but nobody designs right to the code minimum. We design over these minimum numbers, and then we have this nasty habit of running spaces in hospitals 24/7, which creates a tremendous amount of reheat above this. So first thing we need to do is stop over designing, stop overflowing air. This picture is real data. This is from one of our hospitals. It's a hospital that's 340,000 square foot, and I'm showing you September to November. So you can see the outside air temperature ranges between 90 degrees and 40 degrees. The design capacity of this system, of all the air systems in the building, is 350,000 CFM. That's about 1.0 CFM per square foot, or 7 air changes if you want to call it that. And that includes a margin of safety, as design always does. So you can see that on a 90-degree day, we do not need all that air. We're only using 270,000 CFM, which is 0.8 CFM a square foot, or 5 air changes. The lowest number on this graph is 240,000 CFM, which is 0.7 CFM per square foot, or 5 air changes per hour. And the reason I'm showing you this picture is because this is the best one that I've found. Out of our 32 hospitals, this is the best VAV system that I've found. So we have the high, the peak demand at 90 degrees in the middle of the day, and then the low, the overnight demand when it's 60 or 75 or 70 degrees outside. In this system, the difference between the peak and the low is 15%. That's a 15% turn down. Now, I have a technical term for that. It's called, you might as well not do VAV, or this is really shitty VAV. Now, I spent a whole year in 2019 collecting data on designs. We did about 1 million square foot of air handler projects in 2019. Every time we did a project, I logged the room names and the square footage and the design CFM into this nice database. So these are the top 30 spaces, top 30 space types in hospitals by frequency. The first thing I want to point out here is all the way at the bottom. Operating rooms are on the bottom of this list of the top 30. Operating rooms account for less than 1% of our hospital footprints. In fact, if you look at all the critical spaces, you sum up isolation rooms, operating rooms, protective environment, the sum of all those critical spaces is less than 3% of our hospital footprint. So for the sake of energy, let's focus on the top 3. In third place is patient rooms. Our average design engineer put in a peak of 9 air changes in our patient rooms. Under code, the minimum is 4 air changes almost anywhere you go, sometimes lower, which is at least a 65% turndown opportunity. The second most common spaces in the hospitals is administrative areas. 20% of hospital buildings are administrative spaces. And our design engineers have been putting in, again, 9 air changes in those spaces. Well, that's a lot of air. We can do a 90% turn down there under any code scenario that I know within the country. And then, of course, the single most common space in hospitals is corridors. We have miles and miles of corridors. There's a quarter mile of corridor for every 100,000 square foot of hospitals. And our design engineers put in an average of 5 air changes, which is a lot of air. The code minimum is 2 air changes. So that is a 60% turn down opportunity between the peak and an overnight minimum. So let's go back to this chart. The average code minimum that you're going to find throughout hospital buildings is about 0.5 to 0.55 CFM per square foot, or 4 air changes per hour, 3.7 air changes per hour for the volume of the space that you're looking at. In California, we can drop this off a little bit because we have some different rules in the patient rooms, but that's not a huge effect. Generally, that's a number that you should be targeting for your occupied code minimum. The average code minimum at night is significantly less. Some of these spaces can shut completely down. Most of them can turn down. So you should be seeing about 0.4 CFM per square foot, which is more like 2.7 air changes an hour for the volume of your spaces at night. When it's 65 degrees at night, 70 degrees at night, that's where you should be running. And then the overall average minimum exhaust is about 0.25 CFM per square foot, which is around 1.5 air changes for the volume of the building. We tend to run our bathrooms 24/7, and that generally drives the overall ventilation equation. Code minimum outside, by the way, is significantly lower than this. It's only 1.15 or 0.2 CFM per square foot, which is just about 1 air change. So this is what VAV should look like. When it's warm outside, we should be seeing our peak air. But when there's mild temperatures during the day, we should be riding down at that daytime code minimum, and every night we should be seeing a solid drop off in our air quality, or our air quantity, I'm sorry. The point of this slide is to stop blaming the code. You have to do what you have to do. I hear design engineers constantly complaining that, oh, we can't do energy efficiency because the code is limiting. But then we find in the hospitals around the country constant volume systems or really crappy VAV systems that do not turn down. And so I said at the top of this presentation that most of the energy that we're wasting is not code related. It's design practice related. This is what I mean. Yeah, and I focused on air here because air really sets the demand. If you design an air system that turns down to 40% every night, then you'll see the chiller and the boiler energy and the reheat energy follow that, of course. So that takes us into the second part of this presentation, which is the critique of the code, or the critique of our national standard. I have been critical publicly of ASHRAE Standard 170, the air change table. It is an outdated paradigm, and most of the numbers in it are not credible. Before I go too crazy on critique, let me say there are areas in hospitals where HVAC systems need to do some pretty clear things. We have a few clean spaces and some airborne containment. The clean spaces are operating rooms where we want clean air to mitigate surgical site infections, protective environments for severely immune compromised patients, and then we also have pharmaceutical compounding where we're mixing up pharmaceuticals. Then we do have an example of doing containment. That's an airborne isolation space. If you don't know, there is a very short list of the quote-unquote bona fide airborne diseases, and they're shown up here: tuberculosis, chickenpox, measles, mumps, rubella. As of today, coronavirus has not been added to that list. So when someone is suspected of carrying one of these airborne diseases, we isolate them in a room that's exhausted and held at negative pressure. right? Now, since it's 2020, I'm going to digress for about 3 minutes here to talk about airborne and droplet. I think at this point, clinicians and policymakers and nurses and mechanical engineers alike can all agree the terminology here is very confusing and very bad. We call droplets anything larger than 5 microns, and then airborne diseases anything sort of smaller than that. But the terminology is very confusing because droplets are in the air. One writer in the popular press said, "What do you mean a droplet's not airborne? It is clearly borne by air." And that's true. As a ventilation guy, though, I think back to this diagram. In the 1950s, William Riley proved that tuberculosis infects through the air. He put guinea pigs in a chamber and vented them from a TB ward. Those animals never touched the patient, never saw the patient, never in the same room as the patient. They only shared air, and when they caught TB, so the virus had to move from one room to the next chamber through the air and cause an infection. And I hope you can see this is way scarier than coronavirus because social distancing simply would not work. In the media, there was a lot of talk about the basic reproduction number, or the R0, which is the base of the exponent for the pandemic, right? Every case causes R0 new cases. Makes it the base of the exponent. So for coronavirus, they're saying it's between 1.5, or 1.4 to 5.7 new cases. Well, by comparison, those classic airborne diseases, tuberculosis, measles, chickenpox, you're talking about R0s of 10 or 12, 15, measles as high as 18. So they're significantly more infectious than coronavirus. If you never have to be in the same room to catch a disease, that's where you can imagine an entire apartment building getting infected. And so far, we don't think that's what the coronavirus is, or we haven't seen anything that says that's what the coronavirus is. And to that, I say, thank God. If we legitimately had a measles 2.0, a new infectious disease, airborne, with a base exponent of 15 that hit, I mean, you could just imagine what that would do to New York or San Francisco or Toronto or Mexico City. That is really a whole different ballgame, and emergency preparedness for this is much, much different. Okay, so back to our regularly scheduled programming. A couple things that we can say about this slide. First off, you can put clinical citations on all of this slide. And I'm not talking about ASHRAE journal articles. Everything on this slide can be cited to the clinical literature. Second, no matter what country you're in, if you're looking at the US standard or the French standard or the German standard, everyone honors these basic principles of healthcare engineering. And then finally, to go back to the energy slide that I showed a little while ago, the grand sum of these spaces is less than 10% of our footprint. Now, in the US, we have codes that cover a lot more rooms than this, right? This is only, 5 or 10 rooms out of our table, and we have 100 rooms in our table. So where do we get the requirements for all those other rooms? Well, that's a really good question. In 2015, ASHRAE sponsored a research project to, quote, determine the scientific evidence behind Standard 170, end quote. The research team looked at the 887 requirements in National Standard 170 2013 version. They gathered up all the articles they could find. They collected 1,000 studies and articles and papers. They graded the quality of all of them. And this is the final pie chart. 20% of the requirements were called rational or basic needs. About 1% could be cited to clinical standards. The rest were just rational or procedural. They did find evidence that pertained to about 7% of the requirements in our standard. But when I say they found evidence, that doesn't mean that the evidence supported the number in the standard. In fact, 1% were counter to the evidence and needed to be changed. Another 1% were enhanced practices. In other words, our standard is overkill. But the huge piece here is 73%. 73% of the requirements in our national standard, there is no rational basis, no clinical basis, and no available evidence. This study is free for ASHRAE members, so you can all read it. The URL is right there. The air change rates, which is what I've been talking about and has a big impact on energy and reheat, did very, very poorly in this study. Almost all of the outside air rate and total air change rates had no evidence basis, no clinical basis, and no rational basis. Here's the unfortunate truth if you don't know it. ASHRAE standards are consensus documents. The numbers that we have in our standards are not there because they are valid or they've passed some sort of threshold of scientific or burden of proof. There's no burden of proof. They're there because they win the vote. We have a committee, volunteers on the committee, and they vote on the standards. So this creates this sort of false credibility effect. In the field, we tend to give these requirements a lot more credibility that they deserve because they're written down, they're in the standard. And we figure, oh, you know, the geniuses or the men in the high temple and the white tower that write these standards, in their great wisdom, wouldn't have put a bad number in there, right? So barring something categorically undeniable, you know, we should be following that. But the truth is, it's a popular vote, and it's written by folks that are really very similar to you. So then there's this. This is the California Energy Commission research project. I call it the South Bay project because it took place at one of our hospitals called South Bay Medical Center. We converted a set of constant volume high air change spaces to variable volume and tracked air quality. We put sensors on the wall and tracked temperature and humidity and VOC and CO2 and particles. We got this huge data set, 73 locations, 6 months worth of data, so 8 million data points. And the charts that you're looking at here are from the patient rooms. You can see air changes per hour on the x-axis and contaminants on the y-axis. A couple amazing things here. This data very quickly debunks the idea that 10 air changes or 12 air changes is better than 2 air changes. That is just not true. You can see the levels are pretty much the same under those airflow regimes. If this surprises you, think about it this way. You're wearing a shirt, and before you wear that shirt again, you're going to wash it. You can wash it one time, and it'll be clean enough to wear again. Now, you could continue to wash it. You could wash it 5 times or 10 times or 30 times, and it'll still just be clean enough to wear it again. It really doesn't get any better than clean enough to wear again. It's the same with air quality. We don't need a whole lot of air for hygiene, right? We need 1 air change, maybe 2 air changes tops, right? That's all you need for contamination control and air quality. So our cooling systems are often going to take us up to 6 or 10 or 12 air changes, but that's not making the air a whole lot cleaner. The other really amazing thing about this project is that we're the first people to do it. You would think that after talking about air changes for 50 years, somebody would have checked whether those air changes do any good in controlling contaminants in the environment. And it turns out, whoops, they don't. So here's how I'll wrap up on Standard 170. This is the chart I've shown before. This is the standard air change rate in X-ray rooms plotted against the actor who played James Bond. Sean Connery is, of course, smoking a cigarette, which was fine in an X-ray room in 1964. We've always used 6 air changes, right? There was one code cycle where it shifted to 10 air changes, kind of like that one movie that has George Lazenby, but then it goes back to 6 air changes. And this is also where I point out that most of the X-ray rooms we've built in the last 30 years are not in hospitals. They're in doctor's offices, which are B occupancy. And in B occupancy buildings, there's no 6 air change requirement. So most of the time that we build an imaging room, we don't use this number. And there's literally no reason to. It's a number that no one can explain. We've been repeating it for 50 years, has no evidence basis, no rational basis, no clinical basis. We're just mindlessly repeating it. Now, if you're the type of person who likes to mindlessly repeat numbers because somebody told you to, that's fine, but that's not me. When a rule of thumb is silly or it makes no sense, I say throw it out. So, in closing, I don't think that net zero hospitals are a myth. I think they're attainable. I think they're attainable in the near future. This book cover that I'm showing, I'm not sure what the release date is, but it should come out this year. And I was part of the team that worked on this. This is a guidebook towards net zero energy hospital buildings that ASHRAE did in cooperation with REVA, the European Federation of Mechanical Engineers, HVAC engineers. And I'd highly recommend you get your hands on it. It has a lot of very practical advice and some good context to look at. So to sum up my message, most of the energy we waste in hospital HVAC is really not code related. It's related to our design and our validation practices. So as design engineers, we need to stop blaming the code, take responsibility for what we can't take responsibility for, and start doing a whole lot better with what we can. And second, critique the code. I think it's perfectly fine to critique the code. To many of our designers, we treat these things like they're sacred, but really it is an ASHRAE standard. And if you're a member of ASHRAE, that means it's your standard as much as anyone else. In the long run, I think we need to be accountable and responsible for making sure that the numbers that we have in our code are quality. That's it for me. And I believe now we go to the virtual question bank.